Hello everyone, myself Sonu Kumar, PhD scholar from IIT Indore. Here I am going to present my paper HYDRA, a resource-efficient hybrid data multiplexed runtime layer reconfigurable compute engine for DNN acceleration at 90th ICIIS 2025 conference that is going to held in Sri Lanka. So I am going to acknowledge my collaborators and co-authors, that is Komal Gupta, Isru S. Dasanayake from Sri Lanka, and Mukullo Khende and Santosh Kumar Vishkarma, a professor from IIT Indore. Uh, Here are the outlines with that we are going to explain, in which mostly I am going to cover motivation part, followed by introduction. Then after that, problem statement of the work. Also, what contributions is done by me and my co-authors. Also, what methodology I am going to follow for my work. Then after that, performance evaluation and conclusions and future scope for what type of application we are going to target. Then come to the references. So first of all, we come to the introduction part. Here we are seeing the overview of artificial intelligence, in which we are seeing that the broad picture in which deep learning comes from the neural networks part, that is comes from the brain inspired learning, and that is also the coming from the machine learning and artificial intelligence. So here basically we can say that the artificial intelligence is the basic building block in which we are going to study about the deep learning, that is the smallest part, and in which we are seeing that the deep learning are the part of the broad field area of AI, and that from that we got the brain inspired computation, that is the program that takes functionality from the way brain works. Also, the output of the neurons are called activations, and synapses are the often referred as weights. And then we come to the deep neural networks that is capable of learning high level of features with the more complexity and abstractions. Then the DNN accelerator test on real life images, and results will be evaluated. So here we have the clear picture of the whole neural network architecture, in which we saw how the image is coming from as a form of the input, in which we saw the clear picture pixels form, and that comes that convert into the pixels, and that in the form of input features. Then it convolute with the kernels, and after that convoluted features passes through the input layers of the fully connected deep neural networks. And how the computation works, here we see clearly, in which also the hidden layer presents, and after computation with the hidden layer, we got the output from the output layer, and then we recognize what type of the input, and what is the type of the images. So, what motivates us to work on this? Like we see everywhere, the autonomous driving, drones for security, natural language processing devices, object detection and classification, everything required the artificial intelligence nowadays. So, for that, DNN accelerators and their massive computational demand still requires the resource efficient optimization and parallel architecture for computational accelerations. Also, the realization of ANN with the large number of neurons is still challenging a task, because we are seeing that everywhere surrounded with the data, and the data requires the huge number of computation. For that, we need smaller neurons that computes large data. So, in deep learning, MAC operation accounts for more than 90% of the computational power. So, it is still a challenging task to how to overcome from this bottleneck. So first we come from the problem statement, as I have referred one paper, that is ACM threads, and in which we see that the work is using the neurons single layers, in which we see that the some task is still under utilization, which show the power utilization is high, heavy resource due to the nmax with the n activation function. So these are the bottleneck from that paper. And also another paper that I am referring from the neurocomputing, in which they are using different layers but a single activation function with the every layer, in which we say how the work is computing and passing through the every layer serially. So on that, they lost throughput at once clock per period in each layer computation. Also delay over it come. So on seeing these bottleneck from the both the paper, I am making one solution in which I am designing 1D layer reuse and hardware reuse architecture, which try to overcome the both the bottlenecks. So key contributions here, I am defining my work, that is the layer reuse and AF reuse, in which it is combination of the both the layer reuse architecture and AF reuse architecture for the optimization of the work. So first of the we take the conditions in this timing machine, and which we see the how the work is flow. So replace n activation function with the single activation function first. Then after that we save n minus 1 activation function blocks. So moving forward, a small latency increases via piezo, as we see the we using one single piezo between the neurons and activation functions. So sequential nature of DNN fits hardware reuse architecture. Also, it takes a huge activation function utilization that makes the large area savings. So also it gives the lower static power and simplified control. So basically, we are seeing that the on using the layer reuse architecture and AF reuse, we are saving the n minus one A blocks that saves the area, and also low power computations. Also, it gives the low latency. So here is the full architecture of our device, proposed HYDRA, in which we see how the work is flow. So here we are seeing that we have one piezo block between the activation function and our FMA unit, and that the data is passing through is serially, and then again they come back mm, through the input layers. And also we are seeing in FMA block we have multiplier and accumulation, in which our data is pre-bias loaded. That is also our novel contributions. And for that we are giving the 64 parallel FMAs per layer, and with the single activation function for use via piezo. Also we are control unit which manage the layer sequencing for sequential purpose. And also we have used ping pong buffering for weights and activations. So on using these, we are getting the low area, low power, and shorter critical path. So we are going to how we are using these works. So I am telling about the methodology, and where we see clear picture of the layer multiplexed control engine, where we see how layer done and done work. Also, in which layer we have to see the output and input muxing. So first we have to load weights plus activations. Then we move for the parallel FMA computations. After that, serialization activation for AF. Then we move for the output buffer and fade to the next layer. So in this way, we are using our work and moving one step other. And at last, the way we have used pre-bias load RN plus RNA for our MAC unit. So also in that part we are using user defined constant, in which we are seeing that the layer configuration is 196, 64, 32, 32, and 10. Also max count FMA per layer is 64, and a single activation function with 5 layer. Also FMA bit width is 8, that is fixed point, and types of the integer bit is 3 with sign bit. So these all are the overview of the architecture. So now come to the performance evaluation on accounting of the work. We are showing the hardware utilization report for the proposed FM and SOTA works at different quantized bitwidths, in which we see we see how our work is different and upgraded from that previous SOTA works. That gives the accountability of the LUTs 87 versus 130. That is the 33% lower than the SOTA works, and delay that accounts 1.30 nanosecond versus 3.81 nanosecond, that is 3 times faster than the previous work. Also, power delay product, it gives 3.92 picojoule per second, picojoule, and that is the 6 times better than the previous work. Here we come for the Mac 8-bit Mac ASIC results, in which we show that the area, power, and delay comparison, and 5-bit to 16-bit quantization show minimal accuracy loss. Also, we are seeing here the bit precision, DNN accuracy loss, in which gives similar low loss for the ASIC results. And also, we have test our evaluation for accuracy in MNIST data set and CFAR10 nearly identical for FP32 baseline. So proposed MAC consumes low area and low power. So here come with the PGA resource utilizations for the full architectural works with the compare with the previous work, in which we saw the improvements by in the form of percentage, where we saw the slice LUTs give the 88% resource saving and slice registered 93%. Also network on chip power, it gives the 0.025 watt, which is 95.8% reduction. Also, it storage the 0 VRAM usage, and it is giving overall the good architectures. So also we come from the quantitative analysis for HYDRA with prior works, in which we test our results on the FPGA board, that is Vertex VC707, and that is the custom model, and give the 8-bit precision, in which we saw how the LUTs comes from like 13.5K and registered 7.9K, and that gives the up to 29 times LUT reduction versus prior works. Also, it has zero DSP usage, and power consumption is 0.25 watt. Also, it gives the better efficiency, that is 7.04 gobs per watt. So, conclusion and future scope, I am here concluding my work that HYDRA achieves greater than 90% resource reductions. Also, it gives the 15 times improvement in power efficiency, and it is ideal for edge AI and tiny ML for different application like city surveillance. We can also use for border surveillance, or any image classification camera, or electric vehicle motors. Also, it is scalable to larger models. So on this, we can say that our efficient design DNN architecture, that is HYDRA, is better for this artificial intelligence era, and we can also future scope, we can use this for ASIC realization and try to convert these work in the fabricate to the 28 nanometer on TSMC, 28 nanometer TSMC. So these all are the references we are using for our work. So thank you. And if you have any queries, you can contact me or my professor Santosh Kumar Viskarma on the given below link. Thank you.